Hey everyone, good evening, guys. No audible, sir. Am I audible, guys? I'm so sorry. Is my voice loud and clear to everyone? Awesome. Awesome, guys. Thanks for the quick confirmation. Good evening, all. Good evening, guys. Good evening, everyone. So, today we have some interesting things to discuss. Let me quickly share my screen and we can get started, guys. Perfect. Okay, so we will be doing dimensionality reduction today. Perfect. So we will be discussing the dimensionality reduction, guys, in which the major algorithms will be the PC and LDA. Dot what we will discuss today. Now this looks the okay. Dimensionality reduction is the today's agenda, and we will be talking about two algorithms. One is principal component analysis, and linear discriminant analysis. A good list of Python books are available at GitHub. Okay, thanks. Thanks so much, Adit, for sharing that. Byte of Python, automated, boring stuff with the Python, beginning with Django CMS, Django e-commerce. Awesome. Thanks for sharing. Perfect. So let's get started here. Okay, so we talked about the feature engineering yesterday, right? Yes, we talked about the feature engineering yesterday. Awesome. And in feature engineering, we talked about two major things: multicollinearity and significancy. And ideally, we understood the overall objective, right? We need to reduce the number of features. Basically, dimensionality reduction. Why it is called dimensionality reduction? Dimensionality reduction means we are trying to reduce the dimensions. And what is a dimension? It's a number of columns. So if we have two columns, we will plot it in two-dimensional plane, right? Yes. If we have three columns, we will plot it in three-dimensional plane. Now, similarly, if we have n number of columns, that will be n dimensional space. Yes. So the number of columns are actually equal to the number of dimensions for us. Yes? Number of columns are actually equal to the number of dimensions, right? And why actually dimension needs to be reduced? Because higher will be the dimensions, more will be the more will be the complicated, more algorithm complicated, more the algorithm will get more complicated, right? More will be the number of dimensions, and more complicated the algorithm will get. Yes. So it's always a good choice to have some reduced number of dimensions or some reduced number of columns. Okay, now how to reduce the columns or the how to reduce the dimensions? That is basically we need to take care of multicollinearity and the significance here, right? We work with the multicollinearity and we work with the significance. Now let's talk about first algorithm, that is PCA. PCA, right? Let's discuss about the PCA first. Now PCA is again a dimensionality reduction algorithm, right? It's a dimensionality reduction algorithm that will reduce the dimensions in the data. It will take care about the multicollinearity but not the significance, and what we need to do with the significance, we'll talk about that later. What is what exactly is the use case where we need to use the principal component analysis? Suppose we have some data, right? There are a huge number of columns, hundreds of columns are available in that data, and while doing the EDA, while doing the feature engineering, we found out that most of the columns are quite similar, they are highly multicollinear. Make sense? That could be a possibility. Yes guys, right? We have hundreds of columns, and while doing EDA, while doing the feature engineering, we found out that most of the columns are very correlated. They are very multicollinear. So in that case, we need to remove the multicollinearity, and dealing with multicollinearity in the columns, in hundreds of columns, is quite hectic thing. It's quite hectic. So in that case, what we can do, we can simply use principal component analysis. Now, hear me out carefully here. Principal component analysis will not select or drop the columns, right? You have, let's suppose, 250 columns. For example, I have 250 columns. Okay. So principal component analysis will not select or it will not drop any column from those 250. It will recreate a new data, right? It will generate some principal components. And now what are these principal components? From these existing data, that means we will be having some n cross 250 dimensional data. N is the number of rows, right? We will be having some n cross 250 dimensional data. From this data itself, it will recreate some new columns. It will generate some new components, some new columns, and those columns will be completely independent to each other. So we can select or drop those principal components later on, right? What principal component analysis will do? It will not select or drop the existing columns, the columns what we have in the data. Rather, it will recreate some new components. It will recreate the data, it will generate some components, and those components will be completely independent to each other. There will not be any multicollinearity in those new generated principal components. And then we can utilize those principal components. Understood? Make sense? Yes, it will create a new, new numerical columns, means completely new data, new principal components. How it will generate those principal components, we'll talk about that. Yes, it will create some new data. Okay. If I just quickly, show you how it will happen. Suppose this is our data. This is our data. 250 columns and n number of rows. After doing PCA, it will recreate this data, right? It will recreate this data, where we are going to have 250 principal components. These are not our columns. These are the principal components with the exact same number of rows. And these principal components are going to be completely independent to each other. That's what PCA does, right? 250 columns itself is complex. Creating new columns, it will become more complex. No, it will not be some new columns added to 250. From that existing 250, it is little bit organizing those 250 columns. Yes, it will change the values. Excuse me. Yeah. So it will actually change the values in those 250 original columns. It will regenerate new principal components, and then we will be using those new principal components. Right? Got the idea what this PCA is going to do? But number of columns will be same. Exactly. The number of columns will be exactly same. Yes, please let me know what's your question. Trainer PCA, find the span, that span of space, this data. Are you trying to say PCA? I'm sorry, I actually didn't get your question. Exactly. The number of rows will also be exactly same. It will just transform this 250 columns into 250 principal components, and those principal components will be completely independent to each other. Right? But it won't be like the first principal component is having anything related to the first column. No, this won't be like this. The first principal component is having something related to the first column. The first principal component will take the entire data and just generate a new component. Right? We can definitely do the dimensionality reduction. We'll talk about that, how the dimensionality reduction needs to be implemented. We will see how it will reduce the dimensions. We'll come to that part, guys. As of now, are we good with this part only, that we have 250 columns? After implementing principal component analysis, we are going to have 250 principal components, and these principal components are going to be completely independent to each other. Is it clear, everyone? Yes? Perfect. Now let's understand how this process will take place. Sure. We have 250 columns in the original data. We will implement principal component analysis. It will regenerate 250 principal components from the existing 250 data, right? And these principal components, please ignore this chat. Try to put your questions in all participants. I understand the questions. Okay, is anyone sending any questions privately, guys? A small request to everyone, please make sure we send the questions to all participants so that everyone should be aware of if there is anything going on. Okay, let me come back to the topic, guys. We have 250 columns in the original data, right? When we implement the principal component analysis, it will generate 250 principal components. Okay, and these principal components will be completely independent to each other. Right now in these columns there is some dependencies, there is some multicollinearity, but right now in these 250 principal components there will be zero multicollinearity. This is what PCA does, and these 250 principal components are completely different than this data. They are being calculated and we will generate them statistically. The rows are going to be exactly same, n. The number of rows will be exactly same. Clear? Yeah, we will understand more, and we will also understand it more better when we'll understand its process, how these principal components are being generated. Okay, so are we good with this part? Number of columns, no, right now the number of columns we have generated is exactly 250. It's exactly 250. Yes, it will generate exactly 250 principal components. Yes, guys, clear everyone? Awesome. Awesome. Okay. Now, in order to understand the principal component analysis, we need to understand few terminologies. So the variance, the amount of variance explained in one feature to other feature is actually the amount of information explained, right? Suppose this is the data distributed. Okay, suppose this is the data distribution. Make sense? Suppose this is the data distribution. I need to extend the axis. Okay, suppose this is the data distribution, this is x-axis and this is y-axis. Now, if we plot this data to x-axis only, if we plot this data to x-axis only, so the data will be plotted this way, right? Right? Data will be plotted this way. Yes. And this will be the variance of the data in x-axis. This will be the variance of data on x-axis. Yes. Make sense? Make sense? Okay. Now, this data originally also have some variance. This data originally have some variance also. Yes. If we plot this data distribution to x-axis only, so this x-axis will have some variance, and this original data, like this data also have some variance, like the amount of data, how the observations are scattered. Yes, how the observations are scattered, that's something we call as a variance, right? So this originally like this original distribution also carries some variance, and when we only plot it on x-axis, this also carries some variance, but definitely the variance what we have in x-axis is going to be less than the variance what we have in y-axis. Yes guys? Yes, makes sense? Perfect, perfect. But what we can say, the overall variance what this data is explaining, sure. When we consider this data distribution with respect to x and y axis both, when we consider about the data distribution in x and y axis both, so this data have some variance, right? This data have some variance. Yes guys? But when we only plot this entire data on x-axis, so the variance what we get in x-axis is going to be less than the variance data originally have in both the dimensions, in both x and y-axis. Yes, variance of x-axis, what variance we have at here, only the data at x-axis will be going to less, this variance will be less than we have the variance of x and y both, means in this two-dimensional plane. Yes? Make sense? Okay. Now suppose its original variance is x, and I should not use x, I should use some other number. Let's say its original variance is z. Okay? The original variance in the data with respect to x and y dimension is z, and the variance at x is explaining 60% of z. That is also possible, that what is the overall variance in this data, the x-axis is capable to explain 60% of that variance. Make sense? Make sense? Yes? Everyone? This makes sense? Okay. Now, Similarly, there will be some variance at y-axis. Sorry. There will be some variance at y-axis also. Yes, guys, there will be some variance at y-axis also. Right? And suppose if the data is plotted at y-axis only, if the data is plotted at y-axis only, so this is again going to have some variance. And let's suppose this is again explaining, I would say 50% of z, means 50% of this entire variance, right? Possible. The 50/60 is not calculated right now. This 50/60 is not calculated right now. It's just hypothetical value. This could be a possibility, right? Yes, it could be a possibility, right? Make sense? Make sense? This 50/60 is not very much calculated right now, but this could be a possibility, right? Awesome, awesome, awesome. Now see, there will be some variance, some common variance that is being explained by both x and y. Yes, if I just consider 50 and 60, if I sum both of them, it will be 110. So some 10% of variance is something that x and y both are explaining, right? Some amount of variance in this data distribution is being explained by x and y both, right? Yes? Yes, makes sense? Okay. And this is what we refer to multicollinearity. This is what we refer to multicollinearity. This is what multicollinearity is. They are explaining the common variance, and that is what is similar, that is what is the relationship between x and y. And this is what we refer as a multicollinearity. It could be more, it could be less, it could be anything. Sure. Sure. See, yeah, I can explain. Definitely, definitely. See, we understood x is explaining some information in this data distribution, y is also explaining some variance in this data distribution, right? Yes. Okay. Okay. Now see, for example, let's assume these are the numbers. 60% is being explained by x, 50% is being explained by y. If we sum 60 plus 50, it comes 110. 10% is extra. Means this 10% variance is something being explained by both. Right? Yes? Make sense? Okay. Other way, if we understood this way, that's perfect. Other way, see, if we change x, we obviously get some change in y as well. Right? If we change the x-axis, we get what will be the possible change in y coordinate. Right? We can relate somehow. If we observe this data, right? If we change x-axis, we have some idea about what will be the change in y-axis, right? Yes, see this data distribution, and x and y are having some relationship. Means change in y can be actually explained by change in x. Even if it is 10%, change in y can, only 10% of the change in y can be explained by change in x, but there is some relationship, right? That is what we refer as a multicollinearity. That's what the multicollinearity is. Okay? Understood everyone about this concept? What exactly we are referring to multicollinearity in terms of statistics, in terms of variance? Everyone? Okay. Now after this, let me show you some figure. Okay. Now see this, guys. See this image. First, just observe the first half. this is the data distribution, and we simply discussed about the projection of this data on x-axis and projection of this data on y-axis, right? We already discussed this. Suppose this is x, this is y, right? The data projection of data on x and y, and that is something we already discussed, right? So this will be the amount of variance explained by y, and this will be the amount of variance explained by x, right? Clear? We already discussed this thing, and this is clear. And amount of variance explained is basically the amount of information explained, right? Perfect, perfect, awesome, awesome. Okay, now what we will do, we will try to find out a principal component. Now see this pink line, we see here. Let me use some other color, or yeah, this is red, but red are the points also. Okay, let me use green. So this pink line we observe here, this pink line, or this green line. Now this is the green line. This is the line that can have maximum possible variance if the dots are projected here. Yes guys, this green line has the maximum possible variance if these blue observations are projected on these lines. Yes, this green line is actually the component, or a linear component, that has the maximum possible variance, right? No, not best fit line. No, I'm not saying it's a best fit line. Just I want to look for a line that can carry the maximum possible variance if that is being treated as a feature, that is being treated as a component, right? I'm just looking for a line that can carry maximum possible variance. Okay, make sense? Does this make sense? We are only looking for a file that can carry maximum possible variance, and we are actually iterating, we are rotating with respect to the mean, and the line will get settled down at a certain orientation where there will be maximum variance on that line. Clear? Clear? Okay. Now tell me, in this data, we have two dimensions. I would say x1, I would say x2, right? So how many principal components we will get in this data? It is supposed to carry maximum possible variance, or there can be any best possible line. The first line it will look, will try to settle down at certain orientation where it can carry the maximum possible variance. That will be the first line it will try to look. Okay? Clear? Yes, basically mean is the center, you can say. Mean, we are actually using the mean for doing the orientation. Okay, maximum variance will be that connects to extreme values, right? Are you looking for the line which has minimum error summarization? No, we are not discussing, guys. Let's not get confused with the linear regression or something else. Right now, just keep it as simple as this. We want to look for a file that we want to look for a line that explains maximum possible variance in all possible directions, right? We just want to look for a line, a linear. You can say we are looking for a linear component, a linear feature that explains maximum possible information in the data. As simple as that, right? We have two dimensions, x1 and x2. We are looking for a linear component, a linear feature that explains maximum possible variance in the given data. Easy? Easy? What can I understand is we minimize the, no guys, let's not put the linear regression here, please. Let's put the linear regression aside here. The cost function, the sum of square of distances, let's keep that thing separate right now. Once we finish PCA, I'll tell you why it is different than that. Once we finish PC, I'll tell you what is difference, what is difference in linear regression and what is difference in PCA. So let's keep the linear regression aside as of now. And right now, it is as simple as that. We are looking for a simple linear component, a linear feature that can explain the maximum possible variance in the data, right? Make sense? Make sense? Okay. Now, when we said in our previous figure, we said that x1 is explaining 60% variance, x2 is explaining 50% variance, we said. But now, when we have this line, I would say this is my principal component one. This is capable of explaining 80% variance. Probably, now this 80% is not calculated. I'm just assuming it is maximum possible. So let's say it is explaining 80%. Possible? Possible? Yes? Everyone? Okay. Now, also refer to this, we have 250 columns. For these 250 columns, we were having 250 PCs. So here also, for 2 columns, we are going to have 2 principal components. And if you see, there is also a perpendicular line that is rotating along with this first principal component, right? There is also a perpendicular line that is rotating along with this first principal component. Yes? And now what is this? This is our principal component 2 that is going to be exactly perpendicular than principal component 1. Now, if this line was explaining 80%, the PC2 will explain remaining 20% of the variance. Yes? Yes? And if you see, we use the components at PC1 and the components at PC2. The components at PC1 and the components at PC2, if we only use these two features, this PC1 and PC2 are going to be completely independent to each other. And PC1 is explaining 80%, PC2 is explaining 20%, both together are again explaining the same amount of information. That means we are not losing any information here. To summarize the end result, what we have, after this, we have PC1, we have PC2, right? PC1 is explaining 80% of variance, PC2 is explaining 20% of variance, right? Means together we are again explaining the same amount of variance without having multicollinearity, without having any multicollinearity, because they are 90 degree to each other. These two principal components are 90 degree to each other. And also, if you observe the points at these two axes, change in PC1 cannot be explained by the change in PC2. Yes? Yes, guys? That's why we are saying they are completely independent. They are completely, they have zero correlation between them. One another way to understand the correlation is cosine similarity. So cos theta explains the relationship between two vectors. If we consider these two as a vectors, the angle between them is 90 degree. Then cos 90 is, what is the value of cos 90? 0. 0 means zero relationship between PC1 and PC2, right? So that is also another way through which we can understand that there is no correlation between PC1 and PC2. Yes, guys. Are we good till here? Means now we understood what is the process behind this. Yes? Now we understood what is the process behind this. Yes? Perfect. We are going step by step, guys. Like after understanding two more concepts, we will understand what exactly this PCA is doing and how it is helpful. Okay, we are going step by step. Now it might not make that sense what exactly we are trying to achieve here, how it is doing the dimensionality reduction and all. But let's stick for a while. We'll do two more concepts and we'll understand how this PCA is working. So as of now, this transformation of 250 columns to 250 principal components and how the transformation is happening is clear by this? Yes? Awesome. And we also understood that these principal components are going to have zero multicollinearity, right? Yes, we also understood these principal components are going to have zero multicollinearity. Yes? Awesome. Perfect. Now, the third step, what we need to understand next is degree of freedom. So before we start anything about degree of freedom, let me know if anyone have any idea about what exactly is degree of freedom. What freedom do we have? What amount of freedom do we have? Okay, now let me explain what is a degree of freedom. Now this is, a little tricky concept to understand and also to explain, but I'll try my best to keep it more simplified. Suppose there is a three-dimensional space. Okay, suppose this is a three-dimensional space. Just think of a corner of your room. Okay, just think of a corner of your room, right? Just think of a corner of our room. Okay. Yes. Yes. No multicollinearity means 100% variance between two PCS. No, zero multicollinearity means there is no relationship between PC1 and PC2. Okay. Yes. Now, if I say the directions of rotation, just think of a pole in our room, and we want to rotate that pole. Make like the condition here is the direction should be perpendicular to each other. So as of now, if I just put the pole parallel to this axis, so one direction is this, right? The pole can rotate with respect to this wall. Yes, one direction is this possible. Yes, this is a wall, and the pole can rotate parallel to this wall. Yes, yes. Okay. Now the another possible direction is also this, at this wall, and we also observe both the directions are perpendicular to each other, right? Both the directions are perpendicular to each other. Yes, both the directions are perpendicular, and there is also a direction this. There is also a direction this. Got it? There are three possible perpendicular directions. There are three possible perpendicular directions in which we can rotate that pole, that stick. Yes? Makes sense? Okay. But if assume if this is the stick, suppose this is the stick, so rotating it with this direction does not make any sense as per the PCA. Yes? Yeah, exactly. X, Y, Y, Z, and Z, X. But if this is the stick, rotating it with this direction does not make any sense as per the PCA concept, right? So either we need to rotate it this way or this way. Yes, parallel to this wall or parallel to this wall, right? Okay, it's getting little confusing. Again, let me try to explain. Suppose this is the pole. This is the pole. Okay, and this pole is parallel to this edge. Suppose. Now, if we rotate it this way, there will be no difference in explanation, right? If we observe this, we need to figure out the possible ways. But if we rotate it this way, we are not doing anything. We are at the same state, right? Make sense? But if we rotate it this way or this way, we are actually exploring the data. Right? We are actually exploring the data. Again, yes, this might be a little confusing, but we need to do a little bit of imagination here. What's happening? Let's suppose there is a corner of our room, okay, and just put a stick parallel to that edge, okay, Now if we can rotate that stick either parallel to one wall or to another wall. Let's suppose this is a room, this is floor, right? This is a floor, this is wall 1 and this is wall 2. Okay, and we put a stick here. So if we rotate the stick like this, we are not actually exploring anything. But if we rotate it this way parallel to this wall, we are exploring the data. Or if we rotate parallel to this wall, again we are exploring the data. Make sense? So in three dimensional, this pole is having 2 degrees of freedom, right? Yes? Yes? Make sense? And also if we observe this was 2-dimensional, this was 2-dimensional, and the degree of freedom for this line was only 1. Yes, the degree of freedom for PC1 is only 1. Right? Right? So this way we can simply say the degree of freedom is actually n minus 1, where n is the dimension. N is the dimension. That makes sense? That makes sense? Sure, please. This degree of freedom part? Yes, n minus 1 is actually the degree of freedom. That's how we calculate the degree of freedom. Sure. We understood this stick and the rotation of the stick. We understood the stick and how do we rotate the stick. We only have two possible perpendicular directions to rotate. Though we can have infinite directions, but what is the constraint? The direction should be perpendicular to each other. So by considering the perpendicular constraint, we can only have 2 possible directions to rotate the stick. Yes? Yes? So in three dimensions, our first principal component has 2 degrees of freedom. Make sense? Make sense? So now let's come to the coordinate geometry. This is the 3-dimensional space. The data is scattered in the 3 dimension, and the first principal component has 2 degrees of freedom to orientate and rotate and to settle down at a certain position, at a certain orientation where it can explain maximum possible variance. Right? Yes. Now in case of 3-dimensional space, there will be data scattered in 3 dimensions. Okay. The first principal component has 2 degrees of freedom to rotate and settle down where it can explain maximum possible variance in that data. Make sense? Yes, guys, make sense? Okay, now this degree of freedom concept, is it clear to everyone? Everyone? Awesome. Now again, there is one more thing to understand the degree of freedom in this. What we discussed right now is only for the first principal component. If we see this 2-dimensional space, the first principal component has 1 degree of freedom, but the second principal component has 0 freedom. It has to be perpendicular to the first, and there is no other, no freedom is available for this PC2. Yes, PC2 has 0 freedom. Yes, PC1 still has a freedom because it's rotating, but once PC1 is settled, PC2 has 0 freedom. There is no other line that can be perpendicular to PC1. So PC2 has no choice at all. So PC1 has PC2, but PC2 has 0. Sorry. PC1 has 1 degree of freedom, but PC2 has 0 degree of freedom in this 2-dimensional space. Right? PC1 is having 1 degree of freedom, but PC2 has 0 degree of freedom. Make sense? This makes sense? Yes, guys? In this, the principal component 1 is actually having 1 degree of freedom. How can we call it 2-dimensional? Because we are actually plotting 2 axes, x1 and x2. But if we see this, there are 3 axes, x1, x2, and x3. It's like a 3D space. It's like a 3D space, and this is like a 2-dimensional space. No, they are lines. They are not planes. They will always be lines. If they are planes, no, they are not planes. They are lines. If they are planes, then the degree of freedom concept will not, it will not be true in case of planes. So they are always lines, even if it is multidimensional. Like actually, why we are getting confused between lines and planes? Because we are trying to correlate it with linear regression. Guys, please put the linear regression aside right now. We are not. I'll explain how it is different from linear regression. In case of linear regression, it becomes a plane, but right now it's a line only. Okay, right now it's only line. Explain by rotation example of PC1 and PC2, please. Okay, sure. So this two dimension is clear. This is two-dimensional space. This is two-dimensional space, right? The first principal component has 1 degree of freedom. Yes, the first principal component has 1 degree of freedom. There is only one possible direction, right? But if you observe the another one, PC2, that has 0 degree of freedom. Once PC1 is decided, PC2 has no other choice to stay perpendicular to PC2. Yes? Got it? So PC2 has 0 degree of freedom. Yes, guys, are we getting it now? PC1 has 1 degree of freedom in two-dimensional space, and PC2 has 0 degree of freedom in two-dimensional space. Yes, guys? Okay, now see this. With respect to PC1, PC2 has 0 degrees of freedom. Exactly. Because why so? PC2 has to be perpendicular to PC1, right? So in case of, let's understand this way. Let me make it more, simplified. Let me make it more simplified, guys. In case of two dimensions, or let's understand in case of three dimensions. In case of three dimensions, there are possibly two degrees of freedom. Yes. Yes. In 3D, there will be two possible degrees of freedom. Out of these two, one will be taken by PC1. Yes. PC1 will take one. Right? Now, how many are remaining? Only 1 degree of freedom is left for PC2. Yes? Yes? Only 1 degree of freedom is left for PC2. To understand this better, let's suppose this pole got settled down at this orientation only. Now, for the second principal component, it is only left with this direction. Right? Right? So that's what happening here. For the first principal component, it was having degrees of freedom. Like 2 degrees of freedom is actually a technical term. In simple language, we can understand two possible perpendicular directions to rotate. Yes? So for PC1, it has two possible perpendicular directions to rotate. Make sense? Yes, guys? The first principal component has two possible perpendicular directions to rotate. So once this will settle down, there will be only one possible direction left. That will be taken like after like PC1 is settled down, PC2 will have only one possible direction to rotate. Now once PC2 is also settled down, PC3 will only have, like it will have no other options to rotate or explore. There will be only one possible line available after PC1 and PC2 got perpendicular to each other. So PC3 is going to have 0 degree of freedom. And this is what we observed in this case. PC1 has 2 degree of freedom, but PC2 has 0 degree of freedom. It was a two-dimensional space, right? Make sense? Now this makes sense, the degree of freedom and other things. Awesome. Yes, guys, is it clear to everyone? You have only and we want to wear a different hat every day of a week. Once you wear any 7 hats, one second day you can choose from the 7 remaining hats. Only 3 you can choose from the 5 hats. So on. True. That's the good example. True, that's the good example. Okay, yes guys, degree of freedom is clear everyone? Okay, okay. So please let me know if there is any confusion about the degrees of freedom. If there is any doubt, any confusion about the degrees of freedom. Is it clear everyone? If it is clear, then we can proceed. Otherwise, if degree of freedom is not clear, we won't be able to understand the further things. Are PC1 and PC2 are columns in the data? No. Again, in order to understand what are PC1 and PC2, we need to go back to this state. PC1 and PC2 are the new principal components what we are generating, new features what we are generating from the existing data, right? And also we observed in this as well, we have X and Y, let me rename it to X2. We have X1 and X2, right? We had X1 and X2, and from these X1 and X2, we generated PC1 and PC2. So PC1, this feature is the PC1, this feature is the PC2. So this is completely new generated feature from the existing data, and these features have zero multicollinearity, and we are not even losing any information, right? Clear? Awesome. So we can extract from categorical data as well. Definitely we can, good question. We can extract it from the categorical data, but it will still use the variance concept only. Okay, it will only use the variance concept. Okay. Awesome. Now let's come to the conclusion how this principal component is going to work. Okay, now let's come to the conclusion, guys. How it's going to be helpful in dimensionality reduction and other things. Okay. Now I just need to erase from here. Okay, let me erase this. Suppose we have 50 dimensions. Okay. Suppose we have 50 dimensions. Now I cannot plot 50 dimensional. I cannot actually plot 50 dimensions. Suppose we have 50 dimensions. Okay, means we have 50 columns. So in order to, the way principal component work, it will try to create principal component 1 that is having 49 degree of freedom. Yes. Yes. And it will try to explain maximum possible variance in the entire data set. Suppose PC1 is explaining 10% of the overall variance. That's also possible. That's also possible. Yes, guys. Make sense? Yes. Okay. Similarly, we will create principal component 2 that is having remaining 48 degrees of freedom. And the amount of variance PC2 will explain in the data will definitely be less than PC1, right? The amount of variance PC2 will explain in the data will definitely be less than PC1, right? It will be less than PC1, 9, 8, 7. It could be anything, but although it's going to be lesser than PC1. Yes, this also makes sense. The variance explained by PC2 can never be greater than PC1. It will be always, lesser than PC1. Yes, exactly. So suppose I put it's 8%, right? Similarly, PC3 with 47 degree of freedom, it is having 5% explanation, right? Then PC4, let's say this will be having 46 degree of freedoms, and it is explaining 3% or 2% of variance. I would say 2% only. Okay. Now see, These four principal components alone are explaining 25% of the entire data. Out of 50 columns, we generated principal components, and only four principal components can explain 25% of the entire information. Right? On the whole data set, not on a particular column, on a whole data set. So if we see this, if we are looking PC1 having maximum variance with respect to X1 and X2 both, and X1 and X2 is our data set, right? Okay, so this is on whole data set. And this way, we can see the four principal components are capable of explaining 25% of the information, right? Right? Yes. And if we proceed, like there will be completely PC 50, it will create definitely total 50 principal components. And I can say at PC 30 or so, some reduced number of principal component will be explaining 90 to 95% of information in the entire data set. Yes. Yes, guys. Some reduced number of principal component, not totally 50, in somewhere in 30s, 34, 35, or somewhere in 20s also, 28, 29, it could be anything, but some reduced number of principal component will explain us 90 to 95% of the entire information, right? Right? Make sense? It's easy for two columns. Rest 5% we can compromise, because that is something we also compromise during the pre-processing step, missing values, outliers, and duplicates. So rest 5% it is something we can afford to compromise. Okay. It's easy for a two column, but if we have many columns, how do we know the PC we select accommodates maximum possible? Is there something else to teach? For all these things, there are mathematical formulations that algorithm will go ahead, right? This is just to this what we discussed. It's basically to understand how PC works, how principal component analysis, how this PCA works, right? So this is just to understand, to have a original foundation, what exactly is principal component analysis, how exactly it works, and what kind of results we are going to get from this principal component analysis. Is it clear, everyone? Yes, the calculations, the generation of principal component and everything will be done by the system. We have the libraries, we have, simple functions to implement all these things, but in order to use it right way, we need to know the foundation. We need to know how exactly it's working. So most important thing is what exactly it is, how it is working, and what it will generate. And I hope these three things are clear about principal component analysis. Yes, everyone? Okay, now what is the overall result? What is the end result? We have reduced columns and we have removed multicollinearity, and that is something more than enough to achieve, right? 90 to 95% of the variance, we can just select the number of principal components that can explain 90 to 95% of the information, 90 to 95% of the variance in the data, right? And why 90 to 95? We can afford to lose, we can afford to compromise 5% of data, because 5% of information we also compromise while doing outliers and missing values treatment. So like 5 to 10% is somewhat okay. We can just select the number of principal component till where we have 90 to 95% of the explanation. Okay. Understood? This method comes under feature engineering step. Awesome, guys. Awesome. All good with the foundation of principal component analysis? Awesome, guys. Okay. Now, LDA is actually easy. Now we understood the PCA. LDA is quite easier in comparison to the PCA, though it has some similar sort of logic. But again, it's way more easier than principal component analysis. So let's understand the LDA then. So in PC1 and PC2 are updated version of the data where there is no dependency of each column. Exactly. Correct. This means we understood. I can definitely summarize, but I think only summarizing will not help because this is, very big and very, very complicated topic. So in short, I can just summarize that principal component analysis is an algorithm that can reduce the number of columns by removing the multicollinearity in the data. How it works, it tries to generate new components, new statistical calculated columns that are having zero relationship between themselves. So for example, we have 250 columns. After doing the PCA, it will generate 250 principal components. There will be zero multicollinearity between principal components, and that's what we concluded here. Right? That's what we concluded here. PC1, PC2, PC3, and like in case 50 columns, and we have 50 principal components. Some reduced number of principal components will explain 90 to 95% of the data. So the number of columns, the number of dimensions got reduced, and the multicollinearity also removed in the data, right? That's what principal component analysis does. Correct? No, not significance. It will not take care about the significance. Only, only multicollinearity. The principal component analysis will not talk about the significance. Only multicollinearity. Yes, got the idea of what exactly is principal component analysis? Okay, for individual data, it will create PCA. Not for individual data. The principal component it will generate is not related to some specific column. That single principal component has contribution of all the columns somewhere. Right? So if you observe this, yes, yes, this also makes sense. If you observe this first principal component, this is explaining something in X1 also, and this is explaining something in X2 also. So this PC1 is actually not something that is related to some some specific feature. It is explaining something in X1 and also something in X2 all as well. Definitely, that could also be a chance that 90 to 95% variance we can get only by the 10th principal component. Definitely, if there is very high multicollinearity, there is very high multicollinearity in the data. Most of the columns are multicollinear, so it will simply get the 10 principal components only. In short, what data is doing, what principal component is doing, it is simply organizing the data into the features with zero multicollinearity. Principal component is only organizing these features with zero multicollinearity. Why do we need dimensionality reduction? Because higher is the there is a phrase in data science, dimensionality is the curse to the model. Any machine learning model, any algorithm we use, dimension is the curse to that. Means we need to have as less as possible dimensions. Higher will be the dimensions, more will be the complicated algorithm. Correct? And also there is no use of there is no point of using lots of similar data, right? Yes, guys, practically also we don't need to have a lot of similar players. Okay. So now let's proceed to the dimensionality reduction, guys. Sorry, the linear discriminant analysis for the dimensionality reduction. LDA. Okay. So again, I need a plot here. Okay, this time I have some straight lines. Okay, suppose the case here is the healthy patients and the diseased patients. Okay, let's take the example of healthy patients and the diseased patients. Okay. Perfect. Now suppose this is our blood sugar level. I'm just taking any random medical factor. This is blood sugar, and this is, let's say, pulse rate. Okay, suppose this is the pulse rate, and red belongs to healthy patients. Red belongs to diseased patients, and green belongs to healthy patients. Green belongs to healthy patients, right? Disease and healthy. Make sense? Make sense? Okay. Now, suppose we want to reduce the number of dimensions to classify this data. Our aim here is we want to reduce the number of dimensions to classify this data. Okay, that's what the dimensionality reduction is. But now we are also taking care of the significancy, means we need to classify the data. That's the overall objective, and anything that supports our end goal, that's called the significancy. So right now we need to reduce the number of columns, the number of features what we have, to get the right classification. Now observe, just suppose I only use blood sugar level to do the classification. So let me plot all the patients to blood sugar level. Now this will be the region for diseased patients. This will be the region for diseased patient. And similarly, if we use the pulse rate only, that is going to be the region for diseased patients, right? That's going to be the region for the diseased patients. And similarly, this will be the region for healthy patients. Yes, and here this will be the region for the healthy patients at x and y axis. Okay, for x and y axis, right? And if we see here, like, we can actually get some right prediction to some data, but again we have some overlapping also, right? At this range of blood sugar, we can't be sure whether the patient is healthy or not, right? At this area of blood sugar, we can't be very sure if the patient is healthy or not. But if it is greater than this, we can say it's not healthy. If it's less than this, we can say it's healthy, right? Make sense? Make sense? But here, we cannot make a confident prediction. And that's also the case in the another dimension, right? Here we can give a good decision, here we can give a good decision, but here we can't be very confident, right? Right? So we just need to look for a feature that can give a good, good discrimination. The name makes more sense here. Discriminant analysis. It is trying to look for a feature that will be better discriminant, means it can discriminate the features. So if I use this kind of this kind of new feature, so that's going to be the region for diseased people, right? And this is going to be the region for the healthy patients, right? And again, there is significant difference. This component, this linear component, can give us more confident predictions, right? Yes. Yes? Make sense? What LDA is exactly trying to do? Sure. If we observe the blood sugar and if we observe this alone pulse rate feature, they are not capable to make a good predictions about whether the patient is going to have a disease or not, right? Yes. The blood sugar and the end objective is to reduce the dimension. We have two dimensions, so we observe whether a single dimension blood sugar is capable enough to make the classification, but we observed it's actually not. And again, we observed whether the pulse rate is capable enough to make the classification, and we observed again it's not, right? So we created a new feature that is this, this black line, where we can see there is a clear separation between the diseased patients and the healthy patients, right? Make sense? Okay, now we got the idea what discriminant LDA is doing. No, 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 no. If we plot everything, that's the same as this, guys. We used this, everything got plotted to this principal component. Now if you plot everything to this line, everything to this line, this single dimensional line is going to get us the right results, right? Yes. When we, the y-x, this coordinate is having x and y if you are looking it at two dimensions, right? Now this is a new feature, this is a completely new feature, and the value at this feature will be with respect to this feature only, right? So if, let me pick some another example. Okay, so right now this information is having two coordinates, right? X and y, x coordinate and y coordinate, right? This data has two coordinates, x and y, x and y. Yes, but when we use it at here only, it is only having one coordinate, x. Yes, okay. Now I removed x and y. I removed x and y, and I created a completely new feature. So let's say this is LD1, linear discriminant 1. So this observation is only going to have one value, that is whatever will be at this new feature, right? Yes, it's definitely it's a one dimension, right? No, it have not reduced any dimension. It is a completely new dimension the way PCA works, right? When we discuss the principal component analysis, we are trying to generate a new principal component, right? And we discussed in principal component analysis, in linear discriminant analysis, in the very beginning that these algorithms are not going to remove or to consider some specific given dimension. They are going to generate new components, new features, right? We are not going to leave the data which are not confident. Our aim is not to leave anything. Our aim here is to generate a new feature that can give a accurate prediction, right? So this new line is a new linear discriminant that can make more accurate predictions, right? So if you see this new line, it can classify everyone. It can classify everyone, right? If you see this new line, excuse me, let me just put the charger. Yeah. Sorry. If we see this new line, this is actually classifying everyone. Yes. If we see this line, this is classifying everything. Make sense? Okay. Now this is what LDA does. Now let's understand how it will do. Okay. This we understood what it does. Now we need to understand how it will do. Okay. Yes, guys. Understood what it does. Now let's understand how it will create this. Okay. So in order to understand how, yes, what is clear? The what of LDA is clear, everyone? Okay, now let's suppose, let me create 3 examples. Okay, and let me draw the data that is taking over. Okay, these are the weights. I would consider another example like this, and I would consider one example like this. Okay. Okay, so there are 3 possible, let's suppose I'm saying there are 3 possible features. There can be 3 possible features. Now tell me, which feature is the best discriminant out of these 3? Which feature is the best discriminant out of these 3? One, how? I'm saying discriminant. Which feature is the best discriminant? Most of the people are saying 2. Why not 3, guys? Why not 3? Okay, I understood where is the confusion. Let me again give you another plot. Okay. Wait, it's actually not less component, guys. It's actually not less component. Let me clarify it with the figure, guys. Let me clarify it with the figure. Okay. Now suppose this is the region. Suppose this is the region for rates. Okay. Or let me not be very specific with the square. Let me just make a free region. Okay, let's suppose this is the region where reds are there. Okay, and this is the region where greens are there. Okay, now this is a possible, yes, and this is also possible. Both are possible. Let's suppose this is 1 and this is 2. Okay, in both the classification can be done. Here also the classification can be done. It is covering more data, right? And here also, let me correct it. Suppose the classification is also possible in this as well. Okay, the classification is also possible in this, and this is also covering more data. And at the same time, if we observe this and if we observe this, which one is more accurate? Yes, guys, in this case, which one is more accurate? 2, 2, not okay. 2, no, why 2? Why not 1? Okay, the aim here is to discriminate. This is the 2 and this is the 1. Aim here is to discriminate here. What exactly is the aim? Okay, got it. Where is the confusion? What exactly is the aim here? To discriminate, right? The aim here is to discriminate, not to carry more variance. Yes, the aim here is to discriminate, guys. The aim here is to discriminate. Yes, both are discriminating, but if you have this, if you have this option to choose the one which discriminates best. So which one will you choose? One, one, right? Okay. Now this way we can say the third is the best discriminator. The third is the best discriminator. Yes, guys. We can say the third is going to be a best discriminator. Everyone understood? The third is going to be the best discriminator. Awesome. Why three, not two inverts? I'll just explain. You will understood in a while. You will just understood in a while. Okay, now there is some concept called between variance and within variance. Okay, so the variance in a given class, this is called within variance. Okay, similarly for this it will be from here to here. This is called within variance, and the variance between the average values is called the between variance, right? Within variance, within variance, and between the average values of both is the between variance, right? Within variance and between variance. Make sense? What is within variance and between variance? Perfect. Perfect. Okay. Now, if the within variance is less, means the observations are more homogeneous in a given class, more similar to each other. Yes. If I say this within variance is less, that means the observation are more similar in a given class. Yes. If the within variance is less, we can say that observations are more similar in a given class, right? And if the between variance is high, we can say the two classes are more different. There is a good difference between two classes if the between variance is high. So ultimately we need to increase between variance upon within variance, right? This fraction needs to be increased, and that's how it will look for a best discriminator. Now got it? Why 3 is better, and why 3 is better than 2? Because the observations are more similar in this third feature, right? Observations are more similar in this third feature that belongs to same class. They are more similar in this third feature than that of second feature. Also, notice here the number of observations are exactly same here. If I would say the red has 70 observations and the healthy one have 73 observations. So here also there are 70, here also there are 70, here also there are 70 observations, right? Right? Make sense? Make sense? Why third is better than 2? Exactly. And the linear discriminant analysis will try to maximize the between variance upon within variance. The linear discriminant analysis will try to maximize the between variance upon within variance. In order to maximize this fraction, the denominator should be less and numerator should be high, and ultimately it will try to generate a better discriminant. Exactly. That's what we want to achieve, Rahul. Exactly, guys. So understood about linear discriminant analysis? Everyone? Awesome. Now we'll talk about the codes part. But before we get into the code, let's understand. Yeah, we'll take a break. We'll take a break, guys. Yes, in order to get a better linear discriminant, we need to increase between variance upon within variance. And in order to increase between variance upon within variance should be minimized and between variance should be maximized. And this way, we can maximize this entire fraction. Got it? Easy? Easy, guys? Okay, this is the start. We are going to have a lot more interesting concepts from next week. This is the beginning. I hope we are enjoying this. Yes, the things are getting more interesting now. Right? The things, the topics are getting more interesting. Instead of understanding that merge and concatenate. Okay, perfect. What is the use of discriminating? These features can be helpful to make the right predictions, right? Once we have a good discriminator, we can easily get to know a new patient, whether this new patient is having a disease or not. Once we have a good discriminator, we can easily make a predictions whether a new patient is going to have disease or not. Sure. See, in this linear discriminant, once we have a good discriminator, we can easily get to know for a new patient whether that new patient have a disease or not. Right? That's what the end goal is. Yes. Yes. Awesome, guys. Okay, so if I would ask what amount of this we understood, like if this entire is 100%, what percent of this we understood? 99. Oh, I'm really glad. 85 to 90, 70%. Awesome, guys. Awesome. 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 Brilliant. Honestly, when I was doing all these things, let me be very honest. When this was the first time all these LDA and PCA was new to me, I literally left. Like I wanted to leave all the state. I was like, I don't want to do data science and machine learning. So if we are getting, 80% or 70, if we understood 80, 70% of this concept, so we are brilliant. We are really going great. Awesome. Definitely we'll see their applications. We'll pick a data set and we will implement and we'll see how the dimensions got reduced and how we achieved the goal, right? So we'll definitely see the codes and the examples. Definitely, guys. Let's go for a break. I'm so sorry. Let's go for a break. Let me start the polls. We we need 20 minutes. Okay. Okay. Okay, guys. Sure. Too much too much to digest, so it will take more time. The polls are open. Let me start the Google timer. It should be 20 minutes now. Perfect. Let's get back after the break, guys. Hey guys, so we are all back. Awesome. So let's start the code. Let's start the code. Where it is, Pandas basics. I think I have done PCLDA in today itself in some batch. There it is. Okay, so we all have the file, and this is the same file what we have been using from the beginning. You just need to scroll it after this what we did, this robust scaling, and we will be starting from here. Before we start, let me clear all the outputs. Zero outputs. Okay, now the very first thing we need to understand is the type of data we have. Okay, so let's see what exactly is the type of data. So now we are using a research data, means that is meant for the research and the practice, called MNIST dataset. The name of the dataset is MNIST. Okay, and this is basically MNIST digits data. So MNIST also have fashion dataset, but we are not working on digits. We are not working on fashion. We are working on the digits dataset. Excuse me. The dataset is in Drive. We don't need to locate the dataset from some external resource. It's already available in the library. Okay. MNIST digits. So we will be using the MNIST digits dataset. Now, what exactly is this dataset? This has the digits of 28 cross 28. Right? This dataset has digits of 28 cross 28. Right? This dataset has digits of 28 cross 28, and yes, handwritten digits. Basically, we have the images of digits, and every image is having the dimensions of 28 cross 28 pixels. Okay, and we have 70,000 such digits, right? Such images, right? We have 70,000 such images, right? We have 70,000 such images, guys. Seventy thousand such images, right? So it's a three-dimensional data. Make sense? We have 28 cross 28 image, and we have 70,000 such image, and every image represents some digit. Okay, this is the data set. Make sense? We have images of 28 cross 28, and we have 70,000 such images, and every image represents some digit, some handwritten digit. Okay, right? Okay, now how many pixels will be there in 28 cross 28 image? Yes, guys, how many pixels will be there in 28 cross 28 image? Anyone? 28 into 28, 784. And we try to make this data into two-dimensional. The data would be somewhat like this: 784 columns and 70K records, right? 70K into 784, right? Yes, that will be the shape of data in 2 dimensions. Okay, now see the number of columns we have. The number of column we have is 784. Very huge. So this could be a possible case for dimensionality reduction. The amount of columns, the number of columns are very huge, 784. So this could be a possible use case for dimensionality reduction. Right? Yes, and 784 is actually huge. It's more than enough, right? Okay. Now, if the data architecture, data structure is clear, I can erase that. Yes, guys. If it's clear, I can erase, and let's move to the code part. Everyone? Awesome. So let me erase this, and this is how we can import this specific MNIST dataset. Though MNIST dataset is already available in sklearn library, so we need to read it from CSV or any external resource. We can easily read it from the sklearn library. So we simply import it from sklearn.dataset, import fetch OpenML. That's library for the datasets. Okay. Now from fetch OpenML, we specified we want to extract MNIST 784. And we are storing the data in MNIST object. Easy? Let me execute this. And let me see. Okay, now the data is huge, so this will take some time to complete the execution. Data is huge, so it will take some time to complete the execution. Let's wait until this finishes. It won't take too much time. It will just take maximum 1 minute or so, 1 or 2 minutes. Now basically this MNIST will have a lot of information. This MNIST object, I thought in my laptop taking time. Yes, it takes time. Yeah, now it's done. Now it's done. It shouldn't in Mac. Ideally it should not, but my system is it's completed its serving period. It's almost going to take retirement. So that's why it's lazy now. Okay, this is the data set. Yes, it served its service period. Okay, this is the data set. If we see MNIST, we have okay, can we understand what exactly is data type? Why for every data set store? Yes, exactly. The target for every data set, if we are importing it from this OpenML or sklearn library, it will be in targets. Okay, yes guys. What is this MNIST object? What is this MNIST object? I got a response, dictionary. Anyone else? What exactly is this MNIST object? Is it like, what exactly is the data type? Dictionary. Yes, this is dictionary. Key and value. So we have key and value. So let's understand the keys in it. So there are lots of keys available. But first of all, let's see the description. Now what's written in the description is the same what we discussed. The data architecture, right? 28 cross 28 is the dimension of an image. We have 70,000 records, 60,000 for training and 10,000 for sample, 10,000 sample for testing. So we have total 70,000 records. Okay, and there is a lot more about this data set, everything. So we understood what is the data description. Now let's observe the data key from MNIST, and this is carrying some array, right? This data is carrying some array, and if we check the shape, it's 784, right? This is 784 columns and 70,000 records. So this is the two-dimensional data what we, what we talked about. This is what we have. This is what data we have that we discussed, right? Make sense? Okay. Now if we check the target is actually having the labels, means the first array, these 784 pixel, if we try to create an image from these 784 pixel, it will display an image of handwritten digit 5 for the first. The second 784 pixels, if we convert it to 28 cross 28, and if we plot the image for these 784 pixel, it will display an image of digit 0. My system didn't loading MNIST. Possible, guys. The data is huge, so it's possible. It's possible, guys. It could take a lot of time. The data is very huge. It could take a lot of time. So if you are using Google Collaboratory, try to change your runtime to GPU or TPU. It will be quicker in that case. Jupyter Lab in cloud. Okay, it will take time. We need to read this data from the Google Drive, guys. We need to read this data from Google Drive. Oh, no, sorry. We need to read it from the library itself, not from the Google Drive. We are reading it from the library only. Yeah, not from the Google Drive. It's there in the library. So, is the data set loaded? Yes, like Boston, like Iris. Is the data set loaded, guys? Or it's still taking time? No, not. Oops. Taking time. So this means my Mac isn't disappointing me much. We can do later. Definitely. Let's do it right here, and you can do it later. Okay. I3. It's I3 gonna take a lot of time. Okay, let's do it, guys. Perfect. We understood what is there in target. Keeping up, yes. Max works well if we keep them optimized. They perform well if we keep them optimized. Okay. Now the shape of target is 70,000. The length of the data was 70,000 images, so it will also give the target for 70,000, right? Now let's store it into a variable. I stored it in X, and this is our data. This is our data. Clear till here? 318. The cell number 318. Awesome. Now let's observe the images, some sample images. So see, plt.imshow is the function to display the images. S0 is the first array. We are reshaping it to 28 cross 28 and we want to display the image in grayscale. Right? We are simply displaying the image in grayscale. Correct? plt.imshow is just to show image. X0 is the first array from X dot reshape, okay, into 28 cross 28, and then color mapping is equal to gray, means we want to display it in a grayscale, black and white. And we can see first target was also 5 and it is also displaying 5. Correct? Error, what is the error? If you are getting key error, do dot reshape, right? Okay, x0, do dot value. Try this if you are getting key error. If you are getting error, try this. My name comes Abhilash 0 to 10, John. Why it's 0 to 10 is there? Sometimes code only work in Jupyter and not in Jupyter Lab. No, it's not like that. It could be because of the library. It could be because of the library. If you are getting module not found error or something, that could be a case. But it's actually not the case if it's working in notebook and it won't work in lab. That should not happen. Current the dataset load command is still executing, but I am not able to run normal codes now. Is that normal? Like we cannot execute anything else once the this is actually a sequential process. We cannot execute multiple cells at the same time. It will only execute one by one. Attribute error. Okay, if you were getting error before key error 0, there were key error before. Yes, and now it's giving attribute error. Okay, can you please paste me the entire error statement? Can you please paste me the entire statement? Not attribute values. Values. It should be values. Have I send you values? It should be values. You named value. Okay. It should be values. Congrats. Awesome, guys. Clear, everyone? Okay. We understood this IAM show and we displayed the data set. Everyone? The first line of code. Sure. Here it is, the first line of code. This code is already there in Google Drive. I think this code is already there in Google Drive. Yes, yes. Okay, cool. Now let's proceed and let's see at the data. Okay, we saw the observations. Okay, Yesterday when we did standard scaling, we discussed that in case of PCA and LDA, we need to do standard scale all the time. There is no other, scaling method. We always do standard scaling before we implement PCA and LDA. Remember? Yesterday or day before yesterday, we discussed this, that every time we do PCA or LDA, we need to do standard scale, right? So now let's implement the standard scaling, one invalid. If you are getting system already, if you are getting system warning, that's the warning. It's okay. Warning is not an error, and you can easily ignore that warning. Okay. We can easily ignore the warning, the way we ignore the zebra crossing at signal, right? Okay, now we need to do the standard scalar, and we will simply do the standard scaling to our data set that is stored in the variable x is standard scalar dot fit transform x, and we stored it in x standardized. Easy, understood? This thing is clear, everyone? From cell number 322 to 326, we simply did the standard scaling, right? Right? Awesome. Now here we will start the real action. We have imported the PCA class. We have imported the PCA class sklearn.decomposition import PCA. Easy. And we will create an object for PCA. Object creation, initiating an object for PCA class. Then we are training PCA.fit X standardized. Now this is the major function. This fit function is actually performing all that creation of principal components and what amount of variance every principal component is explaining and everything. So this fit function is the lead player. This fit function is performing everything on the given data. And also, if now we understood what PCA is doing, how PCA is working, now this also makes more sense that standardizing the data before we implement the PCA is actually a good decision, right? Yes. After we understood how exactly PCA is going to treat the dataset and how PCA will generate the components, this also makes much more sense to standardize the data before we implement the PCA, right? Awesome. Okay, now this function, what we are doing right now, PCA.fit, this is responsible of doing everything. It is analyzing the data. It is looking what all principal components can be generated at different degrees of freedom and everything. So this is doing all the tricky jobs and everything. We don't need to take care about what's happening. We just need to remember this fit function, and it will do everything what we discussed in 1.5 hours, right? Easy. Now I'll simply execute. This will take some time, definitely. This fit function is doing some big things, so it's gonna take some time. Yes, this fit function is going to take some time, but not much. So right now what's happening, whenever we see this, okay, it's done. It's done. Now once the PCA is done, there is an attribute to this PCA object. The same object is having a new attribute here, explained variance ratio. Now this explained variance ratio will tell what amount of variance every principal component is explaining. And even if I show you the shape, it will say 784, right? So what exactly it is doing, it is telling what amount of variance every principal component is explaining. And there are total 784 values, because ideally we discussed this thing that if there are 250 columns, it will generate 250 principal components. So there was 784 columns. It generated 784 principal components. Okay, right? Easy, easy. What is this explained variance ratio? So it means no dimensions were reduced. Not so far. Not so far. Not so far. Okay. So it have now 784 principal components, and it also has what amount of variance every principal component is explaining, right? Okay, perfect. Now we will simply plot. So what I am doing, I am simply plotting the explained variance ratio and also their cumulative sum. So let's observe the figure. Now this is the explained variance ratio. This first figure is actually plotting the explained variance ratio. Now we can see the first principal component was explaining around 4% of data. Then this keeps on reducing, and at the end we have nothing left to explain. Make sense? The degree of freedom concept, and we discussed the first principal component will try to explain maximum possible variance, and this will keep on reducing and so on. So that's what it is trying to explain in our data set. Easy? It's slightly different. uh, it will keep on reducing. And okay, you mean to say in your file it's different? Yes, post 600 it's almost zero, means 600 components have explained everything here. Now after this there is nothing left to explain. The peak is different. Is it near to 0.04? It should not be different. It's near to 0.04. More than 0.05. And we also have done the standardization, right? Okay, the figure size is different. That should be 2010. Maybe that could be a possibility. Okay, yeah. Yeah. That must be already executed, right? It must be already executed. It must be already executed. Okay. So what is there on y-axis? Y-axis is explained variance ratio. What amount of information every principal component is explaining, right? Okay. Perfect. So this figure is clear, everyone. What we understand from this figure is clear. Now, the second is, let me again change the figure size, otherwise we could have some confusion. Yeah. So now second is the cumulative sum. Do we know what is cumulative sum, guys? Do we know what is cumulative sum? No? Yes? Okay, let me tell you what is cumulative sum. Suppose there is 1, 2, 3, 4, 5, 6, 7, 8, right? And there is cumulative sum we need to calculate. So this will be 1, 3, 6, 10, 15, 21, 28, and 36. If I'm not wrong. Yes. So this is the cumulative sum. Correct? So we simply plotted the cumulative sum. We simply plotted our cumulative sum. Okay. Now we just need the number of principal components where we reach 95% of the variance. We just need to calculate the cumulative sum where we reached 99% of the information, right? Yes, we just need to calculate the cumulative sum till the point we reached 95% of the variance. Make sense? So how do we do this? We simply save the cumulative percentage and check where we reached 95%. So there are 331 principal components that can explain 95% of the information, right? Only 331 principal components can explain 95% of the information. Now, we got the number. How to get 331 principal components? Again, create another PC object by specifying the number of components and simply do the transform this time, right? And this is how the data looks like. Exactly. By half of the data reduced by preserving 95% of the original data. Yes? No problem, no problem. The cumulative sum is clear? The cumulative sum is clear? Okay. Now, we just need to get the number of principal components at which we achieved 95% of the information. Right? Now understood? Awesome. So, we created another instance. So, till cell number 338, we are trying to calculate, we are trying to get how many PCs are required. But right from here, we are trying to transform our data into 331 principal component. And this is our transformed data. So instead of using 784 columns, we can use 331 features, right? Easy? Yes, guys, easy? Easy? Awesome. Now, let me tell you one more secret. Like in upcoming sessions, we are going to discuss a lot more, tricky algorithms where there will be very huge mathematics, derivations, and lot of things. But the coding part will be as easy as this simple fit function and everything is done. Boom. Right? We have mathematics. That's the major thing. That's what we need to discuss. The mathematics, the foundation of the algorithm. But the coding is just this fit function. The coding is only this fit function. We just need to call, we just need to invoke the fit and the algorithm is done. So that's what we are going to have in upcoming, algorithms. But what's the most important thing? To understand their mathematical foundations. This coding will be same. Exactly. This is going to be same for all the data set. We just need to take care about the data set variables and other things. That is something we need to take care about. Rest, the entire pattern, the syntax and everything is going to be same. Right? And also, we don't need to remember the codings, guys. Yes, definitely. Like in upcoming session, in upcoming, the next week is completely going to be the mathematical class. Right? The next week is completely going to be mathematics. Okay, we are going to go back to those 10 standards and 11 standard mathematics. Excuse me. This is something urgent. Hello. Sorry about that, guys. My dad forgot his net banking password. This is a book for statistics. You can refer to that O'Reilly one. They have a good explanation about the statistics and everything. Okay. Yeah. I'll just remind me again at the end of the session. I'll give you the link and everything. Yes, it's going to be a refreshed maths course. Perfect. So yes, guys, are we good with this part? Understood? The PC and everything. This PC is clear. Awesome. Now this is the same PC in single cell. This is the same thing in only one cell. The same PC only. Okay, so before we proceed to LDA, let's talk about few differences about PC and LDAs. Okay, so by the coding part, by the conceptual part of PCA, what type of algorithm it is? Is it supervised or unsupervised? Approx keep it 5 to 10. They are not more than that. Is it supervised or unsupervised? PCA is supervised. Few people are saying unsupervised. Okay. Unsupervised, supervised, unsupervised, supervised. Unsupervised. Classified data range. No, it's not actually classifying the data range. Unsupervised, unsupervised, unsupervised. Okay. What about others, guys? I need more responses. PCA is supervised or unsupervised? Supervised. Supervised. Interesting. Unsupervised. Supervised. Definitely unsupervised. Unsupervised. Okay. Okay. So in order to answer, let me explain what is supervised and what is unsupervised. In supervised, we have the target variable. In unsupervised, we don't have the target variable, right? right? Yes. In supervised, we have the target variable. In unsupervised, we don't have the target variable, right? That's about supervised and unsupervised. Yes, guys. In supervised machine learning, we do have the target, but in unsupervised, we don't have the target. Yes? Okay. Now, have we worked with the target in PCA? Have we included target anywhere in PCA? Okay. Same results. Same answers. So this way, what it is, supervised or unsupervised? Understood? Understood? Clear? It is there, definitely. No, yeah, you are right. The target column is there, but in order to implement PCA, in order to get the results, we haven't used it anywhere. Yeah, exactly. You are right. The target column is there, but in order to achieve the PCA, we haven't used it anywhere. And also, if the target variable is not there, we can use PCA, right? Right? Understood? Easy? Easy, guys? Easy? Correct? We have the target variable in the data, but we haven't utilized it, right? And this means even if we don't have the target, we can use PCA. Can we use the PCA for predictions model? Definitely. Let's suppose we want to predict something, but the input variables are huge. So we can use PCA, we can generate principal components, and we can use principal components to make the predictions, right? Yes? But the data is supervised, it contains target column. Actually, how we can say, like, how we will take a decision whether it is a supervised or it's not a, so it's not supervised, right? Whenever we work, let's say there is a problem statement to make a predictions or something, and those predictions are available with us, right? We want to predict whether there is a cancer or not, and we already have that cancer variable with us, yes or no. So that's a supervised problem. Right now the problem is to reduce the number of dimensions, and in this case having a target is not necessary, right? Yes, make sense. Even if we don't have the target variable, we can implement the principal component analysis. Like right now, we have the target. This data set is definitely a supervised problem. This data set belongs to a supervised problem. But we can also implement this PCA if the target variable is not there. Because in this case also, we haven't utilized target variable anywhere. Got it? Yes, we can do both supervised and unsupervised. Awesome. Awesome. Yes, guys. Understood principal component analysis? I think I got it. Yeah, please let me know if you have any confusion. We didn't include target in PCA. If we look back at the code, we are only using this X, and X was the data, the 784 pixel values, right? We haven't utilized the target in implementing PCA, right? Yes. See, in doing the entire PCA, we haven't used the target variable anywhere, right? So that's why we are saying it's an unsupervised approach. Sure, let me show you the code from the cumulative variance. You mean to say from here? Cell 337? Awesome. Yes, please let me know if there is any confusion, guys. If there is anything what I can help, please let me know. Definitely it will require some revision, some practice, or you might need to rewatch the video. Yes? But in case you have anything, any confusion, anything is not clear as of now about the concept or something, we have to say we are going to use unsupervised learning model for PCA for this data set, right? Okay, let me clarify. See, be it a supervised approach or an unsupervised approach. Let me execute. Let me just delete this. Suppose in supervised, we used to have the target variable, right? The X and the Y, right? That's what we have in supervised approach. And in unsupervised, we just have the data. This is it. That's what we have, right? So we can apply PCA only to X, right? Yes, and this will transform from PCs to Y. Yes, yes, and here definitely we can use principal component. From X we can transform the PCs, principal components, right? And the number of dimensions definitely can be reduced. Yes. So if we observe the PCA closely, the target is, yeah, right, the target is not being included anywhere. We are not including the target anywhere. Even if the target is there, even if the target is not there, we can simply go ahead with the PCA. That's why we say the PCA is an unsupervised approach. Yes, yes. Now got it? Awesome. Can we use PCA for mixed data type? Example contain. Exactly. We all, that's the real case. Like if we talk about a practical data set, we are going to get categories and the containers. So we always do the PC on that. Right? We always do the PC on that. There is no such prerequisite that data needs to be in this specific nature to, use for the PCA. 95% can't be called as a target because if it is 80, answer wouldn't be 331. Yes, the 95% is actually a good to follow rule, right? Because 5% is something we also compromise while doing the data pre-processing, missing values and outliers, right? So we can still compromise 5% of the data here. Make sense? Make sense? And again, this is little subjective for different problem, for different types of data. That is an information we give to its system. Yes, what amount of data we want to preserve after having the principal components and how much data we can compromise. That's what we need to specify. That is an information again, see. Here also, if suppose in unsupervised machine learning, this is unsupervised approach, right? This is the unsupervised approach. We only have X. Yes, we only have X, right? And we used principal component analysis and we transform the data into principal components. This makes sense in supervised approach. Got it? Awesome. Awesome. Okay, now let me just show you the code for LDA. Now the code for LDA is exactly same. There is nothing different than the code in PCA. See, all the steps are exactly same. Instead of PCA, we are importing LDA, and in fit function, we are also giving the target variable. That's the small difference in LDA. Rest everything is exactly same. Okay. Coding pattern of LDA is exactly same. The initial few codes are simply reading the data, doing the standardization, and reading data, doing standardization, importing the library. It's just during the fit we need to specify why also, uh, because the LDA is supervised approach. We need to have target variable in LDA, right? Yes, yes. While we discussed LDA, we need to have this target: how many people are diseased and how many people are healthy. Without that, we can't create linear discriminants, right? Yes, yes. So LDA is supervised. That's the only difference. While training in LDA, we need to specify why also. Rest, entire thing is exactly same. Okay, easy. Yes. Now let me know the questions. Now let me know the questions, guys. We got 331 after PCA, and after fixing 95%, I got the order wrongly for a moment. I'm sorry. Wrong order means wrong order means how do we standard scale for the categorical data? We actually in categorical data we don't do the scaling one by one to every column. We do the scaling to the entire data set, right? And even if it is categorical, the scaling will be done with respect to the mean and the standard deviation. That is something is not, very much, that it's not making a very good sense in categories, but yes, that's how it goes, right? So whenever we standardize the entire data set. After doing PCA or LDA, can we use another model? Exactly. See, this is not a modeling. This is just a data treatment. This is not a modeling. This is not a modeling. This is just a data treatment. Like we are trying to prepare a data for the further models, and definitely we will be using the further algorithms like regression classification on this data. Got it? Awesome. Awesome. Okay. There is the drive. Thanks for this also. Thanks. This data scientist toolbox third version. Yeah, let me also save this. Hadoop. There is a lot of content. Loads of resources. Thank you so much. Awesome, guys. Perfect. So all good with the feature engineering, everyone? All good with the feature engineering? Total for 500 TB content. Really great. We'll try the code this weekend and then we'll come on Monday with the dots. Definitely. And the agenda for Monday, let me tell you today itself. The agenda for Monday will be to cover linear regression, right? Linear regressions, all the aspects about linear regression, how it gets trained, what are the problems, how do we tackle those problems. And I don't think we will be able to implement the codes, but yes, we will try to cover the conceptual part. On Tuesday, we'll do the code. On Wednesday, we'll do the classification algorithm. On Thursday and Friday. Okay, so next week agenda should be to complete entire classification and regression. Yeah, logistic also. The book title, sure. Now let me know what all needs to be shared, guys. It's from O'Reilly. LDA is supervised, exactly, because we also need the target variable. If we observe the way LDA works, we discuss the target is necessary. If we don't have the target variable, we will not be able to implement the LDA. Yes? Yes, guys? Yes, we are done with the agenda. If there are any questions, then we can discuss. Otherwise, we are good to drop off. Thank you, everyone. Thanks all. Let me know if anyone have any questions. Please, I'm open for Q&A. We will study deep learning also. It's up to you. It's up to you. If you want to study, you can definitely enroll for deep learning and you can learn. This is the class I really enjoyed when compared to the previous class. That's because now we are having some good things to discuss. X1 reshape, getting key error. Just use x dot values 1. Just use x dot values 1. We enjoyed this class and we're gonna enjoy the upcoming sessions also, because now we have some interesting stuffs to discuss. And which file today's class notebook is there? Day 4, you will get everything in day 4. Let me create day 5 and upload today's content also. Let me know once you start. Guys, please make sure we spend some time for the feedback, and the same, like, we consider 9 or 10 as a good. Anything below 9 is something is something concerned. So make sure you mention what went wrong and where we can improvise. Today is day 5, right? Okay. And what needs to be uploaded for the day first is this whiteboard. Replace. Replace. Okay. And there is no code file. Still, let me upload the same. Pandas basics. Yeah. Awesome. I think we are all good. So, no questions. Interesting. Perfect, guys. Thank you, everyone. Thank you all. See you next week. Happy weekend. Stay safe, stay happy, stay healthy. Take care. Bye bye.
Thank you, sir, for this wonderful session, and thank you everyone for your participation. I request everyone to kindly fill the feedback survey form and share your valuable comments. Thank you, everyone. Take care.